Okay, let's begin. So today we'll be talking about sorting, binary search, and the tree containers. Okay, and you will see that they are all relevant to login. Okay, previously we talked about things, a lot of them like the pushback is O1, right? But if you push back a lot of things, it's gonna be ON. Okay, if you push back 100 things, the cost will be 100, right? Today we'll talk about log n, which if you push back 1 billion things, the cost will be 30. Okay, insert. Okay, we will look at it. So maybe each time is 30, right? Because this time you have a lot of things, right? You search for some element, it will be 30. But insertion is still going to be even more expensive. Let's take a look. So the first is linear search. Let's say you have an array. Okay, you have an array of elements, and so let me use a laser point. Okay, so what you will do is write a for loop, whether 20 equal to 10, whether 20 equal to 50, whether 20 equal to 30, until you find, oh, it's here, right? So you return this, maybe this position 6, so that you can later access this element or change its value, right? So this is the O1 cost, right? So this is the process, right? So your first position, the second position of the array, the third position of the array is still not equal, right? So because you want to search for 62, for example. So you compute the key with the current value, it's not equal until here it's equal, right? So I think this is pretty straightforward. So why I talk about such straightforward thing, right? So one important task with this training is to get you guys familiarized with C++, Java, Python libraries, okay? So that's why I'm teaching this, right? So otherwise you write a for loop, it's done. So in C++, we have a find function, right? I think it's maybe in the algorithm header, okay? So include algorithm, and then you can use std find, okay? So it will, basically, let's say you have an array. This is a user-defined class full, okay? It's a type array of, it's a array in the stack, by the way, right? So it's 10 elements in the stack, okay? And what we'll do is you will call the find function, where you will give a range that you want to search. Here, begin, end means you want to search from the beginning of the array to the end of the array, okay? Right, and because array is it's a regular array, it's not a vector, right? So you have to use begin, std begin, this array, std end, this array, right? You cannot say array.begin parentheses, array.end parentheses, because it's a regular array, it's not a data structure, okay? And then you search for some particular objects, right? So like here, 62 here, right? You want to search for 62, which is here, right? So we'll put 62 here, okay? And you will put the array begin end, okay? Remember, end is one position after the last position, okay? It's 12, right? So we have 11, but actually the 12th position, okay? And when you give this range, it will search, right? And there are two possibilities. One possibility is found, right? So if it's found, it will return something, right? It will return a pointer, by the way, right? So it's actually a pointer, it's a pointer to the location here, right? Let's say if it's this location, it will return pointer to this element, okay? It's actually a plus 4, if you remember, right? This is a4, okay? And as you can also say which position, you can say array and a full, right? So then you use std distance. What it happens is that, let me try to use pen, okay? Array is this location, okay? And this is your location, right? A plus 4. A plus 4. This is A itself, right? So if you compute that distance, it's gonna be 4, right? So you move here, 1, 2, 3, 4, okay? So the index is also 4, right? If you put the first A location. And let me use later again. Okay, so this is std distance, right? And this is how you can all operate on the array, right? Using begin and distance and find, okay? And the find operation can also work on vector, of course. Just give the iterator, right? Which range you want to search, what you want to search, right? This is an ON operation, okay? And if you don't find it, it's same as later we will see in dictionary, for example, which is in C++ called map, okay? If you cannot find it, it will return the end, okay? If 4 is not equal to n, it means, for example, if it means it's in one of those locations, 0, 1, all the way to 11, right? Of course, it's a pointer to this location. It's A plus 11. It's not 11. Okay. If it's equal to n, then you go to the else branch. Okay. The else branch is saying that it's not found. Right. If it's not found, you will go to this location, which is A12, which does not exist. Right. So keep in mind, n is really, some element that is after the last element in the data structure, okay, in your data container, right? So it's exclusive, this inclusive in the beginning, okay? This is almost always happening in all the programming languages, all the data structure, except for maybe I think pandas, right? Pandas, they have some, maybe that designer was not aware of this practice. They have the last one also be inclusive. Okay, I think one of the function I once used. Okay, otherwise everyone follow this tradition, right? And yeah, I'm not sure whether this is locking. Okay, so let's see. So in Java, it's the same thing, right? Java, we have the as list, right? Then you can put an array here. This T is an array, right? So Java has two utility classes. One is called Java utility array, okay? When you have an array, you should put a regular array in Java, right? There's also another class called collections, we'll see later. Okay, if you use collections, then you will put data structures, containers, like Arraylist, right? So just like in C, right? We put regular array, or we put the vector, right? So it's the same idea, okay? But they need this kind of utility class to help you to process those arrays, okay? So here, the reason is actually very simple, okay? The reason is because C, you can have this kind of function as a general function. Java, everything should be wrapped inside a class, okay? So you cannot have a global function, right? So you here, anything related to array is put into the Java util arrays class, okay? So list of function. But one thing is doing is that it can return an at list. Basically, it will return a list object, right? Then this time it wrap into a container, right? So your input, the array is a regular array, the output is a container, okay? Like an array list kind of thing, right? And then for this container, you will have the index of operation, okay? So that's not for regular array. So you have to convert an array into a container so that you can use the index of. Index of, as we will see later, is really just look at the first element that equal to O, okay? And then return you the value, the result, okay? The index, the position, right? Here you see also there's another difference. Java has no pointer, so everything is a pointer, right? And so index of, basically it says C++ will return you a pointer to this element, right? A plus 4. Java will just return you 4, okay? It's a false location. Java has no address concept. It's hidden everywhere. It's used everywhere, but it try to hide it from you. It just makes things more confusing. That's why I don't like Java, right? And so another important thing is that if an array is sorted, okay, we will see that later. You can use binary search directly on this array for this value. Okay, we will talk about later. Keep in mind what we are looking at here, the values are not sorted. Let's say 60 is larger than 20, right? And then suddenly another 90 is also larger than 20, but it's not sorted in any, okay? Here it's the same thing. So yeah, so here's the example of array list, right? So we will see the container array list, just like C++ vector. It does have an index operation, okay? It will return you the index of the first occurrences, okay? It can only return the index of the array, okay? Which position in the array, right? So it cannot return the pointer because Java has no pointer, right? So this is the first occurrence. Even if you have, let's say, 3 20s, it will return you the first 20 position, okay? And what if it has no elements there, right? So because, you know, in C++ we use the end, which is the one after the last element, right? So in Java, so because, you know, the index or the positions are always 0, 1, 2, right? So you say use the -1 to mean if it's not contained, then this index of will return you -1, which means you cannot find the element in the array, okay? And you can do this in the reverse way, right? So last index of, right? Because this index of basically is the first index of, right? So this is the same thing, just starting from the last element, scan all the way toward the first element. And the first time you meet an element equal to O, you take it, right? So another thing you can pay attention is that those kind of Java operation, you don't need to really specify a type, okay? Actually, they all take the object. If you give a specific element, it will compare that specific element because the object is a generic array, a generic pointer, right? It can point to any class that you need. Okay, it's down there. It's just an object class, right? And this is the kind of similar to, you know, in Python, right? Python, you can, in an Arraylist, in a list, you can save different elements, right? Java, you can also do that, unless you specify the type. The Arraylist is all integer, then it's a different story, okay? But for C++, you cannot do that, right? If you want to do that, you need to make it a pointer array, okay? An array of void stuff, as we said. Okay, so Python, right? So Python also has this, right? So you have a list, a Python array is basically a list, right? Okay, so for the list, basically you can also say something like, I want to search for the element. Again, you can search from the sub-range. I want to search from the third element to the fifth element. I want to see whether between these elements, I have a value equal to my search element, okay? Right, so it's the same. So here's the example, right? So if you look at, this is a list of characters, right? So again, unfortunately, Python has no characters, right? So it's all strings, right? So single quotation, double quotation, both strings, right? And then you want to get the index, right? So you know that it's a, let me see. Yeah, I think there's a typo. Okay, this example I copied there. This should be 1, right? So because this is 0, 1, the first element you see is 1. Okay, it's the index of in Java, but here it's Python. It's the same thing. Okay, first. Okay, and if you say, hey, I want an I, but I start from the fourth location. So this is 0, 1, 2, 3, 4. I start from G. I search for I, right? So 4, 5, 6. I will return 6. Okay, and you can also give an end range 3 to 5, right? So 0, 1, 2, 3. 3 is inclusive, 4, 5. 5 is exclusive, okay? So start and is inclusive. So I only look at O and G, okay? And I want to find I. I cannot find it. So it will say value error is not in the list, okay? If you have a question, just stop me anytime, okay? Otherwise, I will be very fast. Also mind that you can use the in operator, right? So for example, whether, let's say we have the alphabet, then we can say whether E is in the alphabet, right? If you say E in alphabet, it will return you true, right? Because it's in the alphabet. If you return B in alphabet, it will return you false, okay? But keep in mind, when you use in, if the list is super long, it will be time consuming, right? 1 billion element, you scan the 1 billion element, right? So it's just a writing a for loop internally, right? So it's just that programming language has those things that save your writing a lot, right? This is why I do the training. It was make your coding maybe 10 times faster than someone who don't know these libraries, right? They write for loops, okay? But it's internally the same thing. Another important thing is that these functions are so user-friendly. Once you see the name, you know what it's doing, right? For loop, you need to understand it, right? So there are two functionality of functions, okay? So the first functionality is to reuse, like this, right? You can use it 1,000 times and just make it a function. Another very important functionality, even if you just use it once, is that you should name them, okay? Like maybe this, you have, let's say, for example, I'm working with Sami on a example of called Mascasian code and standing their code. So what they organize is this, right? They have different stages. So first stage, they may call it, for example, like data generator. Okay, the second stage, so they have a lot of time, mini batch is handled. Okay, the second stage is called maybe proposal generation. Maybe they have a lot of region proposals where it could be objects and there's a lot of overlap, right? Say within a person, right? We want to remove some of them, right? The third is called detection layer. Then we want to also compare this with the Y label we have, okay? And so anyway, so this is kind of maybe you cannot follow what I'm talking about, but these are the different stages of the problem, right? But they all give them a very high level name, okay? Once you see the name, you can describe different stages, but each one could be 40 lines, okay? If you don't give the name, you make these 40 lines, 40 lines, 40 lines, 40 lines, and make it all in one function, right? This will be 160 lines, and you don't know how to, decimate them, right? So where the boundary, what is each doing, you have to read these 40 lines to understand, right? So even if you are not using it twice, try to make it a function, okay? Then function name should be descriptive, right? So then you have the hierarchical structure, then you kind of know what it's doing once you see the function name, right? And there's also comments. And if you really want to change the function, then you read the code, right? So this is how you make your code user-friendly, not just to others, but also to you, because you might need to change. Let's say the first work is done in 2 or 3 months, and the next piece of work, you don't follow it up, right? You totally forget what your code is. You have to reread your 160 code if you don't have these as names, okay? And now, after linear search, we talk about binary search, right? So why we talk about binary search? Because it's faster, it's way faster, right? So here is example, right? Now you can see that our array is really sorted, okay? Let me try to avoid using zoom, okay. Just use a pen here. You can see 4, 7, 8, you can see the values are sorted, right? From small to big, okay? So you will have an upfront sorting cost, right? So, yeah, Sami?
Yes.
What's the upfront sorting cost?
I don't recall, Professor.
Okay, so that's terrible. Okay, this should be none by, at least if you're not first year college student, it should be none by second year college student. Okay, yeah. And July?
Yes, Professor.
What's the upfront cost for sorting?
Of ON,
ON?
like linear.
That's crazy. Okay, if your ON sort, you can make things sort. Sorting is so different from scanning, right? You just find out whether 21 in the array is ON. Sorting is also ON. It's like a free. Do you understand what I mean?
Okay.
Yeah, it's impossible. Okay. Right. You need to. Oh, this thing should be moved here. Then this thing should be moved here. It's very complicated task. Do you really understand?
Yes.
Yeah. It's terrible. Okay. So none of you understand.
But
okay, so.
Professor, by upfront cost, you mean like what is the upfront cost to sort this array, right?
Sorted, right? Then you can do binary search. Okay. Upfront cost means you have to sort it. It's okay.
Yes.
Because if you don't sort it, it's gonna be something like a random order. Then you cannot stop. If you cannot do binary search. Okay. Firstly you need to sort it. Then on the sorted array you can do binary search. It's okay.
Yeah, but Professor, I misunderstand the question. I mean,
yeah.
You mean what is?
What's the cost of sorting it?
Yeah, I mean, if it's merge sort, is different than some other sort method. If this is the question. I mean, if I do merge sort, is n log n. If I do other types of sort, like each sort method has its own cost,
n log
right?
n is fine. Yeah. So okay, so basically it's n log n. Okay. Yeah.
Okay.
If you really understand all the sorting algorithm, you will know that we really just look at quicksort. Okay. Right. So I will talk about.
Yeah. I mean, I like, because some bad choice for sorting is ON, I think. So this is not the best choice, but
no, ON is better. Bad choice is n square. Okay.
N yes, square also n square.
And log n and n. Okay. It's okay. Right?
Yes.
Yeah. And it's super fast. If you scan once, you get it sorted. That's crazy. Okay. And what's the search cost after you get it sorted?
Binary search login.
Yeah, binary search login. Okay. Yeah. Okay. Let's continue then. So these things should be so intuitive that you should just instantly get it. Okay. So here is the example, right? So if you want to, just like a dictionary, right? You want to look for a word, because these words are ordered alphabetically, right? So you will know where the first page or the next page, last page. Then you will just go to the middle page, right? And you see, oh, unfortunately here, you think the middle page is not here, right? You think the middle page is here, okay? Right, then, oh, my word should be after this. I should continue to look at the second half, okay? These things are killed, great, okay? And now I'm here, the first page, the last search is this, right? And now I will, again, go to the middle, right? And then I find, oh, okay, 62 is larger than my range. So these things should be killed. I continue search here, right? So these things are killed, okay? And finally, we have these two words. And of course, the first, last, and you take the middle. When you take the middle, all the program language we look at when you divide by 2, right? Low plus high divide by 2. if your low plus high is 5, okay, divided by 2 is 2.5, right? But if it's all integers, this is integer, this integer, it's actually round down to 2, okay? So this is what C and Java is doing, okay? Python kind of, you need to say this, right? So this means this kind of thing, right? So otherwise it's regular divide, it will be 2.5, at least in Python 3, okay? And because, this is 13, divided by 2 is 6, right? 6.5, but actually 6. So you get this element, you see, hey, they are really equal, okay? Then you find it, right? So you can do 2 actions to do that, right? So the first is, after you find it, you can return this position so that you can change its value, okay? Right? Like this is your object, and you want to use it, and you may update it. This is one thing, right? Better not update the key, by the way, right? If you update the key, you need to move around, right? So your key is static, then we can update its value. So sometimes you need the pointer, the position to be returned. Other times, if you just like whether 22 is in this list in Python, right? You just want a true or false, okay? Then that's just treating this as a set, okay? Then that's actually just return true or false. There are 2 options. Right, here is an example. So what you will have is that you have a low position, and you will have a high position, which is 8, okay? And then you will compute the sum divided by 2, which is 4, which is the middle element, and you see, hey, middle element, I want to search for 45, right? And this is 38, anything below it is killed, okay? I move to the next position, which is my previous mid plus 1, okay? Mid plus 1 is fine. And then now that you know your 2 pointers are changed, right? So you know your low is here, high is here. Then you compute the middle, right? So this is 13. So we know that the middle is 6.5 actually, right? So the mid is 6 now, right? So and then you see this 6 is 77, right? It's larger. So anything from it and even larger should be killed, right? So your high is updated to 6 minus 1, okay? Which is fine. So now your low and high are equal. And if your low and high are equal, that's basically saying that, right, so you are pretty much here, right? Me or here. So this is 45, right? And you are also 45, then you find it. If this is 45, but this is 42, right, you don't find it, okay? Right, so this is very simple, right? So you find the middle element. Floor is usually because all the language are uniform, right? And of course, if it's smaller than or equal to, if then suddenly your L is larger than R, then of course it should return. Okay, it's impossible, right? And you just so if the middle element is smaller than T, right? T is the search key, okay? Then anything from M and even smaller should be killed. Your lower bound should move to M plus 1, okay? Else, if the middle element is larger than key, right? So then M plus 1, M plus 2, all these locations should be removed. Okay, your upper bound R should be removed to M minus 1, okay? And finally, if both are not the case, then it means the else branch means they are equal, right? If they are equal, you just return, right? If you, after all the search, right, so you cannot find it, just like the previous example, instead of 45, you find 42, okay? Then you just return unsuccessful, right? So this is the example here, of course. We will return like a stdn, an end of the array, right? So, and we may also return something like minus 1 in the location, right, in Java, if you remember. So what is the search cost, Sami?
A log insert.
Yeah, why?
Because we're not searching all the elements, we are dividing it by 2 half every time. So
yeah, exactly. So it's very simple, right? So each time you kill half, next time you kill half, right? So let's say you have n elements, each time you kill half. The second time you kill half square. The ith time you kill half I, okay? And finally, you will locate into 1 element, right? How many times do you need to kill it? Cut by half until you reach 1, right? So this is n equal to 2, okay? So the number of iteration I is equal to log 2n, okay? Any questions? And log n is very small, right? If you have 1 billion, log n is 30, okay? Right. So compare with scanning using 1 billion as ST defined, now using binary search, it's just 30 each time. So okay, it's way, way faster, right? And of course, you need to pay upfront sorting cost, right? But if you need to search for 1,000 times, why not pay that cost? N log n, okay? So n log n is saying that if you scan it once, it's n, okay? 30 is log n. It means like you scan 30 times, okay? You can already pay this cost to make them order. After that, for the rest, maybe 1,000, 10,000 search. It will just be 30, not 1 billion, okay? That's so nice, right? So that's why sometimes you need to do binary search, but sometimes you don't, okay? For example, yesterday I'm working with July on this thing, right? So July tell me that he just need a particular kind of events. He pass them once and picks them out, right? And usually what we do is we actually index these things into a dictionary. This is like a binary search tree, okay? It's like then we can do some binary search. Okay, it's hash table. We'll see that later, okay? But if you just do that once, right? You just have one query. Then there's no benefit to you at all, right? If you sort them, for example, then that's even worse because this is 30 times n, right? It's log n, n log n, okay? It's even like do 30 times more, right? Even if you don't sort them, right? There's no improvement, okay? If you just do one query. It's really if you do this kind of query many times, okay? Right? If you just do once, 1 billion is okay, right? Okay, so this is the idea. Another important thing to pay attention that once you sort it, these keys cannot change, right? It's a static array. We'll see that later. Okay? Yeah, so these numbers you should immediately remember. Okay, so right, so you know, so 2 to the 6 is this, right? So 2 to the 9 is this. Most importantly, this thing you should remember. Okay, right? And actually, you should also remember something like a 6. This is 5 6, right? So this is actually 2 to the. This is short. Okay, if you have a short, which is 16-bit, it's this range. But if you can remember 32, that's crazy, right? So there are too many digits, right? But this 10, you should immediately know them, okay? And you see, so 2 to the power 10 is approximately 1,000, okay? That's also why 1 KB is 1,024 byte, okay? 1 megabyte is 1,024 KB, okay? So in computer, we want something to be 2 to the power something, right? So 2 to the power 10 is always close to 1,000. And this, you should always know, okay? So here comes back why login is so important, right? So originally, if you sort, you use stdefine, you need to search for 1 billion elements, okay? Now, if you have login, let's see how many elements you need to search, right? So 1 billion is 1,000, that's 1,000 times together, okay? And you can approximate a little bit, right, to this, okay? Right, and this is what? This is 2 to the power 10, okay? This is what? Then this is 30, right? Okay? And now we know that this thing is 2 to the power 10, okay? We know log 2 and 2 to the power are reverse operations, right? Inverse operations, just like a matrix inverse, right? So they can cancel each other. So it's just 30, right? So now if you pay 30 times this cost just to sort it, now for the next 10,000 queries, each time you just look at 30 elements, not 1 billion elements, okay? So this is why login is so important, binary search is so important. Any questions? So login is very, very important, okay? All this lecture is about login. Unlike previously, we just talk about an array, right? Now we talk about how to do additional stuff on it. One thing to notice is that we do break the cache locality, right? We jump in the middle, jump back and forth, okay? So there's no cache locality for binary search. All right, so how do we do binary search? Let's say in C++, right? So again, we know that in C++, we don't need to wrap a function inside any class, right? So we can have a global function, right? This is the kind of binary search we talk about where it will just tell you whether it's inside the array or not, okay? It's like a Python's in operator, whether in A is in your list 1, something like this, okay? And it returns a Boolean, right? Another thing to keep in mind is that maybe your array, so these iterator pointers point to your array. Your array is an integer array. That's fine, right? We know how to compare. But sometimes you have your user-defined class, right? You have the student name and student grade, okay? Then which should be the key, right? You need to write a comparator function, okay? The comparator function is equivalent to when it should be smaller than, right? So you write a function to say, hey, if the student surname is, let's say, smaller than the other student's surname, return true, right? It's really smaller than, okay? Oh, unfortunately, just one moment. I forgot and I used let me try to get control of my mouse. Okay, I lose control of my mouse. Oh, my mouse is here. Let me try to reach here. Okay, finally I got back my control. Yeah, I think it's crazy. I mean, why Zoom doesn't work with slides well, so I had to use pen. Okay. Also pay attention to this, right? So if you pay attention to this, you know that you only need to define smaller than relationship. Okay. Once you define smaller than a relationship, then you automatically get equal, right? So when A is not smaller than B, B is also not smaller than A, then it makes equal. Okay. And you can also derive, once you have equal, you automatically know what is smaller than equal. You also know what is larger than equal. Okay. So all it requires is smaller than. Okay. This is also the case for all the language. Okay. And here's another thing, right? So you need to pay attention that we have a constant. Let me try to use this later. Okay, we have this constant, right? So, if we search, we will not change the value we want to search, right? This is one thing. Another is reference, right? So the reference is because maybe you are not comparing just an integer, right? Integer is fine, but if you are comparing with a big object, as a student with a lot of subjects, each has a grade, right? So now you just want to search for the student whose English is maybe 100%, 100 points, right? So then you need to say, hey, I compare with points. Then if 99 is more than 100, you define this function here, right? Just to look at English grade, right? You know when it's equal to 100, okay? And then just look at the English grade of the object, right? So then it's a big object. If you don't have the reference, it will be a copy, right? So that's why you need the reference, okay? You don't want to deep copy the object into a local stack and then do the binary search, right? You directly use that as a rename. All right, here are the examples, how to do that. So as we talked about, so firstly, you can have vector, it acts constructor, which is the iterator, right? So you can say, hey, this is array, my array, this is the last element of the array, right? So this, yeah, and I create this array, right? So, and we get this out, okay? So this is one thing you can do, right? So from the beginning to the end of it, right? So keep in mind, this is +9, and there are 9 elements, right? But this is still exclusive, okay? Because this is +1, okay? It's +0, right? It's 0, 1, 2 to 9, right? So if you think about this is 0, this is really 8, okay? So 9 is 1 after the last position, right? So even for arrays, the last element, 9th element does not make sense. It's an array outer bound, right? But when you go to vector, it should +1 to mean this is the iterator to that and of the last element, okay? And then you can sort it, right? So we will talk about sort later. Okay, it's so simple, it's TD sort, right? So if you don't know it, you write your quicksort algorithm, that would be great, okay? And this is also very efficient. If you write your like insertion sort, bubble sort, that's even crazier, right? It's n squared, okay? And so another thing is binary search, right? So you can go from a beginning to end, which means the whole range. You can also search for subrange, by the way, right? We want to search for the element 3, okay? Right. And before doing that, you need to sort that, by the way, okay? If you sort that, you will find, right? Of course, there will be 2 3, right? They will go to here together, right? It will return you, I don't know which 3 it will return, but it will return one of those 3, okay? Because it's sorted, right? Another way you can do is you can sort by your function, right? So the function is actually, defining how to compare these 2 elements in this array, right? It's basically smaller than, right? If I is smaller than this, my function will say, hey, this is really smaller than. If I put it here, right? So this thing can be a function, okay? Compare can be a function. It can also be a class. if it's a class, you need to define the operator, which is parentheses. Okay, basically, if you have a parenthesis, oh, I lose control again. I'll try to avoid that. So. Okay, if you, let me see. If you pass functions, right, this can be a function pointer, right? This is one possibility you can put it here, okay? Just to define a function, the function name is actually a pointer to the function block of the instructions to compile, okay? The second option is that you can define a class, okay? Class something, but you define an operator parenthesis, okay? And then you compare these two elements smaller than, right? If you define this operator parenthesis, it will act this class. If you have an object of the class, it will act like a function. Okay, we will see an example later. Do we need to look at these elements? Yeah, so this is the result. Okay, so let me pull it down. So this is the result. Jalal?
Yes, Professor.
Can you see my mouse?
Yes, no.
Then maybe I don't even need to use anything else, right? The mouse is, you can see it, right?
Yes.
Yeah, that's great. Okay. So basically, this is a Boolean, right? Binary search also returns a Boolean, okay, whether it found or not, okay? So this is just a saying yes or no, okay? Right, so if true, if not, right, false, okay? Right, so now we also have two functions. One is called the lower bound, one called the upper bound. What they're doing is that it will return a pointer, right, iterator, or we can say, to the first element in the range, which does not compare less than that, okay? So what that means is basically saying that, let's say, if you have, let's say, 1, 2, remember we have 3, 3, right? And after we solve 4, 5, 5, 6, 6, right? And now, if let's say we want to search for 3, right? And we want to get the lower bound of 3. What it does is that it will find the first elements in the range. So you see, so the first element of 3 is here, right? Again, this function has to be sorted, and you can do this. Okay, it's still binary search, and this will be returned. Okay, this will be the return value of this value. Okay, it will point to this element, not the second element. Okay, this is the first, what the first means. Okay, it's this element. The second is it does not compare less than value, right? So it will return anything from 3, 4, 5. Okay, right? So 1, 2 will not be. The first that is starting from at least 3, less than or equal to 3. Okay. Now, what if you call the upper bound also put 3 here, right? So what it will do is still the first element, but it will be greater than 3, right? So it will not consider 3. Okay, it will be anything starting from bigger than 3. It will return 4. Okay, the first element that is larger than 3. Any questions? Okay, so you might be confused why this is still binary search, right? How to check this, right? So this is very simple. Okay, so let's say you can let's say you have the start and you find the middle element, which is 3, right? And fortunately you have 3 before it. Then instead of just checking this, you will check the element before it, right? If it's still 3, then which means okay, I need to continue to this side, right? I don't continue this side, right? And when you check the next element, you also check the previous element, see whether they are all 3, okay? So just do some additional O1 time processing, you will make sure it's first element, okay? These details can be easily worked out when you write the code. But again, it's done for you, so you don't even need to do that, okay? So here you can see this is the example again, right? So we have the begin and we want to find 20, right? And remember, call lower bound, upper bound, you all need to sort them first, okay? So here's the value before sorting. Here's the value after sorting. So 10, 10, 10, 20, 20, 20, 30, 30, right? And if you search for lower bound of 20, right, see that 20. If you search for lower bound of 20, it will go to the 20th first position, okay? Position 3, right? Because this is 0, 1, 2, 3, okay? And if you search for upper bound of that, it will go to the first element that is larger than 20, which is 30. Okay, it's this position, which is 6. Okay? Any question? All right, so average. So again, whatever I teach is teaching the methodology. Okay, how people think when they design those libraries. Okay, it's never the particular language. But again, one purpose is you need to familiarize with those language constructs. Otherwise, your coding will be super slow, right? And it's so easy to use a search tree or do binary search, right? So if you write that, if you don't know, you probably will write that code, right? So then your boss will not be happy, okay? Right, so why write it? You already have that STD, binary search, right? Okay, so, okay. And in Java, it's the same thing, right? And here you can see we have two kinds of Java objects, okay? The first Java object is array, right? The second could be an array list, which is an object. This is an array of objects, right? This is a regular array. And if it's a regular array, you will use utility arrays wrapper that has a global functions for operating on those kind of arrays, okay? And it do have binary search. It can also take the starting and subrange in your array and find whether it's in the subrange. Do binary search only within this. Right? This is the key that it's given to you, right? And you need to make sure also before you call this kind of function, it must be sorted, right? If it's not sorted, results are undefined. You can still do that. It will still run the same segment of code, but you don't know what to do, right? You cut to half of them, but that will make sense because some value may be your result. It can go smaller, right? So keep in mind, if you want to use this, sort it first, okay? And if the range contains multiple elements with a specified value, there's no guarantee which one will be returned, right? So talking about this, we need to understand what is returned, right? So if you have 3, 3, 3, unlike the lower bound, upper bound is equal to us, there's no guarantee which one will return. You can return any of these 3 if you are searching for 3 keys, okay? So this is what's happening in the Java library. Yeah, it will return the index, okay? Right, so, and just like index of we see before for linear scheme, okay? And so what's interesting here is that it's kind of merged things, right? So if you find this element here, which is 3, it will return, hey, this is the position of the 3, okay? But if you cannot find it, right? Maybe you want to find 3, but this is 2, this is 4, okay? Then it will return something called the position where you should insert, right? Basically, it will return 3 to you, okay? Return this 4 to you, right? It says, hey, you should insert 3 here, move 4 all the others to the right one position, okay? It will return this insertion point, okay? If it's not exist. So, but to know that, then we need to know whether it exists or not, right? So in order to do that, let's say the index is always positive, right? So we want to encode the insertion position in a way that it's always negative, not even 0, because this is index position in the array can be 0, 1, 2, right? Larger than or equal to 0, okay? So in order to do that, we need to make sure if it does not exist, it will return you a negative value, okay? There's no conflict, right? So this is always negative because insertion point is going to be 0, 1, 2, right? If you take a negation and a -1, it cannot even be 0, right? It's starting at least from -1, okay? Right. And this is actually a very common usage. Let's say if you have x -1, right? So let's say if your insertion location is 3, it will give you -4, okay? But then how do you recover the 3 again? You use this and run this again, okay? This -4 minus is 4, -1 is 3, okay? Then you get back, okay? This operation, if you run twice, it will get back to the original value, right? So this is very convenient and make sure it's always negative, okay? Because this is non-negative, right? So negative value -1, then it's always negative. -1, -2, -3, okay? So basically it's encoding of your insertion location from 0, 1, 2 towards the mapped location return value, which is -1, -2, -3. But if you want to map them back to the insertion point, then you can do the insertion, right? So you can just run this again on this return value, minus that value, -1 again, okay? And so another important thing to pay attention is that insertion doesn't make sense, right? Because after insertion, you need to move all elements toward the right. It's gonna be ON, okay? That's the log-n thing basically is useless, right? Because ON is the dominant, right? ON is 1 billion, right? Log-n is just 30. But after 30, you want to insert, you need to 500 million toward the right. Okay, so that really doesn't help, okay? It's usually we just use it like a false, right? Which means it's not there, okay? If you really need to insert, you can reuse by taking the -x-1, then you know the position. If you can, you know that you only insert once, right? You don't do that often, then it's fine, okay? And you know, if it's not larger than or equal to 0, you know, it's fine, okay? You often, if you don't really need the location, it's fine. If you need the location, you can use array and go to that location position, right? And you can then set A or like say English grade equal to 90, right? You can update, okay? Don't update key, by the way, right? So you can update the values, other attributes. If you don't update the value you compare to sort array, okay? And yeah, so there's a guarantee that if it's positive or non-negative, right? 0 or positive, it's fine. Otherwise, it's not fine. Right? This is more like true or false, okay? And so, you know, this object there's another function you can use, basically the argument with the function, okay? And but it's the same thing, but okay. Yeah, just one moment. I will be back in 10 seconds. Okay, any questions so far? So if you don't understand log n, you are not even understanding computer science, okay? I mean, you are not even there because first-year college students should solve this problem, okay? And the sorting in log n, okay? Everyone should know. Let me see where we are. Yeah, here is the example. Let's go through it. I should not use this. I should use pen. Okay. So here you have an object array. Remember, objects avoid the star in C++. Okay, it's just a pointer to all those values. Okay, right. So you will create those values in heap, and then you point to them. It's kind of like this, right? So but if this is basic types, maybe it's in stack. Okay, the compiler of the Java virtual machine will handle it, right? And then you have the sort arrays dot sort. You can operate on this array, right? And after sorting, it will be sorted, right? And after sorting, you can print them. Okay. Yes, this is a new way of iterator in both Java and C++. You can do that. Okay. In C++, you need a constant, you know, the reference. You don't change the value you took. Okay. And this is the pointer anyway, so it's the same thing. Okay. So you don't have to know this, by the way. Okay. I never use this. So this is more like a Python version of that. You can still use for loop or something, right? So because it's array anyway, right? Right. So this is a number. Okay. So so you can see it's sorted, right? It's 2, 10, something, right? Previous 10, 2. Okay, right? And then if you do binary search, right? You say, hey, I want to search for this value 22, right? In this array, it will return you the position. Okay. Because 20 here, it will return you the real position, which is 2. This is 0, 1, 2, right? The second position, actual position. If you cannot find it, it will return you a negative number. Okay. And as I said, so if you are working on arrays, right? The regular arrays, what you will do is you will use arrays, Java utility arrays. If you are working on data structures, containers, right? They call it collections in Java. It's the same thing. C++, Python called containers, Java called collections. It's the same thing. Okay, it's a collection of objects, right, in this container, right? And for binary search, you can only work on list. You cannot work on like a map or set, those kind of things. Only list. It only works on array, right? Because binary search is basically something related to array. First, so you need to get a middle. If the middle element cannot be get in O1, there's no point. Okay, right? If it's a pointer, it's a linked list. Then you kind of need to go from here all the way to the middle, right? Then that makes much sense. It has to be an array. Let me see. Right. So if you are operating on list, you use collections, right? Otherwise, if it's a regular array, you use arrays. Okay. So these are all global utility functions, but you cannot do that in Java without putting it inside any class. Okay. You have to put in a class. And this is actually this class static function, which means you don't need to create an object for it. Okay, it's a static, which is a function that you can directly use associated with the class. Okay, All right, so let's take a look example of how to use it, right? So it's basically the same, right? So you have an array list. Okay. Oh, I should not use this. Okay. Let me see whether I have no notation here. So if you have an array list in Java, right, you should use n. Okay. Okay. So Jalal,
Yes, Professor.
for C++ vector, what's the same operation? What's the name of it?
Pushback.
Okay. Right. So Latif.
Yes.
Yeah. For Python, what's the operation?
Push. No, append.
Append. Yeah. Okay.
Yes.
It's append to the end. Right. So.
Yeah.
Okay. Yeah. These things you have to memorize, right? So usually you use more, you will remember them, right? If you don't use more, I have to let you memorize these. Okay. If you don't memorize things, you will be in trouble. Okay. You always think you can derive, but actually everyone, these things are their intuition. But for you, you need to think or you need to Google. You know how slow you will be, right? So okay. And right, so collection.binary search, right? Because this is an array list. Okay, we put it here. This area. Okay, and then we want to search for 10. It will give you the location, right? And this is 0, 1, 2, 3. Keep in mind that we don't need to sort it. It's already sorted when you insert, right? So this will be the third location, which is 10, right? And now we search for 13, right? If we search for 13, it should be something here, right? You should add 13 here, right? So this is really add to the fourth location and move 20 to the fifth location, right? So this will be -4, -1, which is -5, okay? But Java has, remember in C, if you want to define, hey, I can just sort them, I can just binary search them, you need the object to know what is smaller than, right? So for that, you can do an operator overload, right? So how to do that, you can Google, right? You need to know there's some way to do that, right? And for Java, how can you do that? So they will have a Java comparator interface. In Java, interface means they are abstract functions. They do not specify what you need to, how you implement the function, but there's a bunch of functions. There's no member variables, okay, only functions, okay? Or in Java, they call methods. And these are abstract methods without any implementation, okay? That's kind of, if you implement that interface, it's kind of force you to have these functions implemented in your actual class, okay? And then these can then be used by some parent interface, right? So you can work on the high level, okay? You know that anything falling under this interface supports those functions, okay? So this is the idea of interface. It's kind of like a abstract function only parent class, okay? It's in interface, okay? It's specific to Java, I think. And so here is an example, right? So let's move it here. Now, for example, let's go back to the next page. First, let's take a look at something here, okay? You see, so now we define an author, right? So if we define an author, then it has first name, last name, book name, right? And now we have so many authors, we want to sort them. We want to first sort them by last name, okay? Keep in mind, it's always last name, right? Let's say we have a bunch of people write a paper, right? Like Diane, and maybe Guimu Guo, and Jalal, right? So, okay, so how do you say this paper? This paper is Yan and others, okay? It's not Da and others, Yan, okay? ETAL dot, okay? Yan and the others, right? So, and then add a citation. And always add a space in between before the citation. But here, if you are using LaTeX, use title, which means this thing cannot go to the next line, okay? If you know LaTeX, right? Which means a space, but you cannot go to the next line, right? So always, and also the bibliographies are always all first sorted by the last name and then the first name, okay? Keep that in mind. You can, if you write something like a da at do, right? So then that's a problem, right? So you are unprofessional, okay? So last name first and then first name, okay? Compare this, right? So let me see where's the, yeah, here example. If you later you need to sort them or you need to do binary search on this object, what you have to do is this, right? I'm trying to get the pen. You need to implement this comparable interface, which put the what you want to compare with here, which is also, right? So then in that case, after you define this, you need to implement inside this class. Okay, you implement another function called the compare_to, right? The compare_to is still the smaller than relationship. Okay, right? So compare_to is still the smaller than relationship, just like what we see in C++, we have a function, right? And here what you do, because it's the author you compare to, so this type will be author. Okay, and what you do is, hey, I first do the last name. This is not necessary, by the way, in C++, Java. In Python, you always have a self here, right? And this self dot if you are inside the class. Okay, that's mandatory. In C++, Java, if you don't write anything, it means the current object's last name. Okay, right. So there are some differences here. Pay attention to that. And compare to this guy's last name, right? If it's less than, then it's done, right? If they happen to be equal, the same last name, then we compare the first name. Okay, so this is like a condition. If this is true, right? So we compare first name. Otherwise, I just use the previous last name, right? Okay, so this goes first and this goes second, right? If this are not equal, we will first consider this. If unfortunately they are equal, we'll consider first name. Okay, so this is what they are doing. And then again, this is not necessary. Okay, it's implicit. And another thing you need to pay attention is after defining this, then you can just do anything, sorting, those kinds of things, right? Because you know how to sort also, right? So then these collections and the arrays, those operators can handle the object, okay? Right, so internally they do a lot of other work, but you don't really need to know them. Let me clear this. I see a dot here. Any questions? This is like a smaller than equal to relationship. Another thing you should pay attention is that you may not know why is this dot compared to, right? Because this is string, okay? This string object itself, those types definitely have been defined the comparable interface for sure, okay? So it's inside its alphabetic comparator, right? So the first character, if they're equal, the second compare, the third, right? Oh, this is smaller than our templates, okay? Right. So these are actually defined internally. Okay, so we are just recursively call they are each member's comparing function. Okay, which it's there. Any questions? If not, we continue, right? So again, you know that in Python we can do something similar, right? We have to. And another thing is that so let me see. I kind of go in the wrong direction. This one. Comparable interface. Now let's look at the collections, right? Collections, you also have the binary search because I think previously it's array, I believe, right? So let me see. Did I just copy this twice? Oh, no. The first thing is actually, you see, it's comparable, okay? Comparable interface. If you define comparable interface, you will call this function, okay? If you don't have comparable interface, but you have defined a comparator function, okay? Then you are actually calling this function. Both are supported by the library. Okay, and they are doing basically the same thing, right? And the comparator function, I think, did we go through that? If not, we will see an example later. Okay. So one thing you need to pay attention is that comparable interface is really it's really like you are just compared to, right? Because your current object is already there. You compare to the second. Okay, but comparator will have a compare function instead of compare_to function, right? Which means then the compare function will say, hey, A compare with B, which one is larger, which one is smaller, right? So they are different. One is a function, one is an object with a compare function, okay? One is just a comparable interface for the current T type, okay? The current T type. Let me see whether we can continue. Right, so yeah, so comparative function. Oh, we are covering it now, right? So comparative function is kind of like in C or Java, right? So for example, if you have basic types, they have defined a struct less for you internally in that library called function, okay? And just to say what it means by operator smaller than, right? So so actually this struct, this object has a operator overloading, right? So as I said, what's the left-hand side, right-hand side, when it's less than left-hand side, right? For basic types, integer, double, string, they're all defined, okay? And so there are new standards, right? So C++ 11, 14, 17, and maybe not 20, right? So early on it's 98, and the next version is 11, 2011. So there are a lot of no change during the period. That's why a lot of old programmers, they don't know these things, right? So you need some retraining, okay? And so the constant expression means, oh, this is really a constant, right? So remember the function itself is actually a pointer, okay? It's a pointer to the second code of the function, okay? So this is a constant expression means, hey, this function cannot change it, okay? It's just a constant that you can call the less operator, okay? That less function, okay? So this is an object with this function, right? It's a member function of this object, right? If you want to define your own object, you can put it there, right? So this is similar. For example, in Java, we have something similar. It's a comparator, right? So for example, let's say we have a class called domain, we have ID, we have URL, right? So, but what we really care is only the comparator object where it has a compare function, right? Domain 1, domain 2, and we really don't care about URL. Just compare with the IDs, okay? Just compare with the IDs. Right? By the way, so this is the one way called the get and setter. You define your object to be private. You don't want any people to update it when they want, and when you really need them, right? So then in that case, you will public return get ID, because that's why they are using get ID, okay? Because now it's in the main function, it's not inside this class, it's private, okay? And here this operator is necessary because you see in your stack you have ID and URL variables, right? Then whenever you don't have this, it will mean these two. When it means this, it means these two. Okay? Only in this case you will need this operator, right? You have the same name in your input argument or in your local variable, then it will mean that one. If you want to mean this one, you need this dot, okay? Otherwise, if there's no name conflict, this dot can be saved. And here, basically, you know, the ID is what? ID is integer. Right? Integer compared to basically we'll call the less function defined for you, okay? Right. So you need to use your informed guess to know which one is defined for you, right? For the integer, definitely it will define for you. But for this kind of object, you definitely need to define it, right? Because who knows you want to compare with IDs, right? Maybe you want to compare with URL, right? So of course you need to define, right? And it's always a recursive call in some way, right? The compare is always defining less than or equal to. Okay? If it's less than or equal to, less than return true, okay, return 1. Otherwise, return maybe equal, return 0, okay? And smaller than equal, return minus and negative, okay? Right, so now what we are doing is this, with this comparator defined, we have a comparator object here, a C, okay? This C can go C, right? And these are the comparator, right? So we can do binary search on the domain with comparator, right? So this is different from the comparable interface, because comparable interface is associated with the object domain, okay? Right? Well, comparator, you can change. Let's say here, this comparator compare with IDs, okay? Right? I can define another comparator to get compare URLs, right? So then it's more flexible. Okay, you're pretty sure your domain, let's say you know that you will only sort by IDs, you can definitely use that. Okay? Another way is that you don't need to provide comparator. You assume domain has a comparable interface. You will try to find it, and then if you have defined a comparable interface, all it will be that function will be. Okay? Any questions? Another thing you need to pay attention is this null, right? You can really for Java and Python, right now you can really point to them because this is not string. This is the pointer to the string array inside the heap. Okay, so here it means you don't point to anything. No. This is pointer. This is the stack. Okay, this is pointer. This is an address. Right? Python has the same thing by set. Okay, so let's look at it. Okay, so I think it's kind of block things. Let me move it down here. So by set left, okay, you can again get a subset list, right? Start and high, low, high in the array, okay? And by default, if you don't get, the low is the first position, high is the length of the array, right? You remember the length of the array is actually, if you use that as index, it's one position after the last element because it starts from 0, okay? And what it does is this, right? So you make sure it's split into 2 halves, right? And your key, by the way, this is the array A, your key is X, okay? So you make sure all the location from low to I, all of them are less than. All means if this condition is satisfied, they are true, all is true. Right? Any of them is false, equal to true. This means anything on the left is, is less than, okay? So it's like a 2, 2, 3, 3, 4, 4. Okay. So I want to make sure if x is 3, right? I want to make sure anything left is smaller than anything on the right is larger than. Okay. Then this position is returned, right? So this position is returned. Okay. So you see, this is exactly what we see in C++, right? So we have larger than equal to, right? So I think it's a lower bound. Okay. And similarly, we have the upper bound, which is bisect right. And the bisect right is equal to bisect. Okay, you can use both. Right? This is larger than. Okay. Right, so this is where we can form steps. Right. And so they also have a combination of binary search plus insertion. Okay. So, but it tells you, keep in mind that log n search is dominated by the slow on. So this is 30, this is 1 billion. Right. Usually we will never use these functions. Okay. But if you really know, you just insert once. Why not? Right. So let's say you have a server you run every day, and maybe every hour you insert some elements once. Right. Then it's fine. Okay. If you have user query 100 queries every second, don't do that. Okay. It's gonna kill your performance. So yes. So how to avoid this? Insertion update, right? How to avoid this update bottleneck, right? Because our array should be pre-started, right? And you cannot change the key, otherwise you need to move things around, right? Insert, you need to move things to the right. Right? How can we avoid this? Jala, how can we avoid this? Hello?
Yes, Professor, I'm here. I'm not sure about this.
Yeah, using another using dictionary, right? Okay. Don't use array. It's okay. Yeah. We'll talk about it's binary search tree or hash table. Okay. Then you can update more quickly. Right. You don't have to update for 1 billion. Okay. Let me see. All right. So this is a way that you can use them and wrap. Let's say you can find left, right, smaller, larger than. Okay. So the next is quicksort. Right. So we talked about if you want to do binary search, the first thing you need to sort. Okay. So again, we will go through some algorithms, but this is not an algorithm training. Okay. This is the data structure training. This is programming training. Okay. I'll tell you, hey, this data structure are there, and you should just call them, and you need to know their cost. Okay. Because this is so important. A lot of people don't know these things. Okay. But good programmers, this is common sense, right? So at least they know these things are there. They can Google. Okay. This is also the purpose of this training, right? So what is quicksort? Quicksort will randomly pick an element, and quicksort will randomly pick and swap to the end. Okay. Then these areas are kind of now what we want to do is segment into 2 parts. One is less than x, one is larger than x. Right? How do you do that? In linear cost. Right. So this is one thing that you can easily do. Okay. This can be typical interview questions to you. Okay. If you want to go to Google it, whatever, right? So the first thing, you randomly sample an element here, then swap with them, right? Then x is here. Then you organize them into 2 parts, right? One part is less than or equal to x, one is larger than or equal to x. Then you want to put back x to the right location. Let's say swap with this element here, right? And this don't need to be ordered because you will finally recursively order them. Okay, let's take a look at some algorithm here, right? So this is what we are doing. Okay. So this is the quicksort, right? So you randomly sample in your country range, right? And then you exchange to the end. Okay, then you do a recursive partition. Oh, this exchanges from the end, you exchange it back. Okay, and this now is in the middle. All these things are less than, all these are larger or equal to, right? And then you recursively call the left part and the right part. Okay, call the same function, right? They will find the middle point and continue to halves. Okay, so this is the algorithm. Again, we will not go into too much algorithms. Okay, so but intuition you should get, otherwise you will never use them. Right? And so what did I do? Okay, so here are what's happening here, right? So what you do is there are 2 cases, right? Because once you swap to the end, then you check the element one at a time. Okay, and you will also keep track of two positions. One is, hey, all the way to I, these elements are less than or equal to X. Right? All the way to J, these elements are larger than X. Right? And I want to continue to check these elements. Right? So then the next element to check is J for them. Right? If it's larger than X, what you do is you increment, right? It's larger. Now I just increment to here, right? Because this element is larger, so larger than X. These segments are all larger than X, okay? Well, if it's smaller than X, right? So let's say in this case, of course you need to insert here, right? But now you know this thing should be in gray, right? So you will move it here, okay, right? And this thing will move to here, okay, right? But let me see. But in that case, you need to increment I because this thing you moved here, right? Let me see how to mention this. So basically, I think I presented wrong. Okay, basically now the J is the next element we check. This is splitting point between all the way smaller than or equal to I is less than X. This is larger, and then we check the next J, right? If it's a gray, it's larger than X. We just move move to the next location. This is larger than X, which is fine. Okay, if it's smaller than X, what you do is first I is incremented, right? So I should move to this location, because you will have a new element which you will move to here. Okay, now not 4 elements, we have 5 elements, right? And then you will swap AI and AJ, right? So you will swap AI and AJ. Remember, I is already here. It's this element. You will swap them. Okay. Now by this time, this element really less than or equal to X, right? Okay. And then J is incremented. Okay. So why we can increment J? Because this is the dark gray is here, right? So this is really dark gray. Okay, we can increment. We still keep the relation. Okay, this is called invariance, right? And then you do this again. All these 3 operations are O3, which is still over. Okay, right? So you can use one pass over the array. You can split it into 2, right? And of course, finally, let's say these are dark gray, these are light gray, right? What you do next is this, right? So let me see whether we measure this. Oh, it's at the top. Okay. So this will be an interview question. Okay, so just see whether you can make such a simple thing work, right? So just some reasoning you will get it. And in algorithm design, in data structures, tons of this kind of thing, right? So it's so complicated, I will not cover them, right? So smart people were doing that and then make them libraries, okay? And always try to utilize their wisdom, okay? So just call the libraries. So the final 2 lines of partition will finish up by swapping the pivot element, which is this element, okay? With the leftmost element greater than X. Let's say all these are gray now, okay? It's done. Now the leftmost greater than X is this. We will swap them, okay? Then this X comes here. All these elements are larger than X. These are smaller than X. Then you recursively call on these. And make sure these left and right are also sorted, right? And this is in between, right? You know that it's gonna be sorted after recursive call, okay? So we know that each time what you do is basically you're scanning once, right? So so each time the cost is n, okay. And even in the very imbalanced case, okay, in the very imbalanced, you are not divided into 2 halves, right? Unfortunately, your sampled points is kind of biased, right? So it's only a small 1/10 is here, 9/10 is here, right? So even in this case, you know, it's still gonna be log n, right? So the longest chain is this, really, right? So let's see why this is the case, right? So this is very easy to see, right? So now you know that you eliminate 1/10, right? So you still have 9/10, right? Still get 90%, okay? And the next time you go down, you have another 9/10, okay? And you come back again, you cut another 10%, right? You get another 9/10, right? So this is really, finally, you want to reach only one element. What is you are doing is 9/10 to the power of I, right? Finally, we'll reduce it to one element. Of course, times the initial length of the n, okay, right? And so if you move it to the right, it's really n equal to what? N equal to 10/9, okay? To the power of I. Iterations, okay? So the tree height is really log 10/n, okay? Just to make this this becomes log. Okay, so even the longest is still log n. Okay, this is a constant anyway, right? So it doesn't matter how you split them, right? But again, it could be so unfortunately you split kind of relative to n. If it, as long as it's 1%, 10%, the complexity whole, right? If it's a n by 3 or something, then this is not so good, right? But the probability is very low. Okay, you can prove that in expectation, the algorithm runs for n log n time. Okay, in the worst case, it will be n squared, like everything is on this line. It's kind of very slow. Okay, so you scan once, and then you get n minus 1, n minus 2, n minus 3. You can scan, just get rid of one element, right? This is square if you sum them up. Okay. And the expectation proof is also in the CLRS algorithm book. Okay, so I will not cover that. Okay, but keep in mind. Okay, so this is expected, right? So there are all different kind of terms. Let's say we have the amortized O1 cost for a pen element in array, right? And for here, this is called the average. Average is n log n, right? So we have worst case n log n now. Heap sort and merge sort, right? So merge sort, you know, you merge, you just look at this and look at this, merge into longer, right? So it's like scanning this once. Each time you make smaller here, move the pad. So you can see that this is log n. Okay. Last time for merge sort, we discussed that, right? So another is heap sort. Okay. Heap sort means you will have a heap structure, binary heap. Okay. We'll talk about what binary heap in the next time, but make sure that you understand what it. Each time you insert, it will be a tree structure. Okay. And the top is the smallest element, right? Each time you just pop it. Okay. Pop it will take O1 time. Then you need to adjustment, right? You pick the largest element here, adjustment along the tree path is log n. Okay. So you will do this n times. Okay. So it's n log n. Okay. So this is intuition. So these algorithms are worst case n log n, right? Kind of better than your worst case n square algorithm, right? But in reality, okay, people do a lot of empirical testing experiments. In reality, Quicksort works the best. Okay, forget about the other side. Okay, even the worst case is not so good, right? It's almost never happen. Okay, especially if you use randomized algorithms, right? So we can randomize it initially. Any questions? So there's a proof. I think maybe it's in the. So there's a proof that if you don't have special conditions, right, n log n is a lower bound. You have to do so many comparisons. Okay, I won't cover it. Okay, but keep in mind you cannot do better than n log n for your sorting. Okay, so this is a tight bound. Quicksort is already n log n if you just think about expectation, right? And so, but there are special cases you can actually get linear time, right? So one example is radius sort, right? You know, let's say you only have 3 digits. Okay, you know the fixed digits. So what you can do is, hey, the first time I sort by the last digit, right? And there's a concept called stable sort, right? So like merge sort, right? So if this comes first, I will always let it come first. I will not swap them. 3, 3. Before sorting, it may be here, there's 3, there's 3. Okay? And then this 3 will come here. This 3 will come here. It will not, the first 3 will not come the second will come the third first. If you have this is called a stable sort. Okay? If you have a stable sort, right? The first time, a lot of sorting algorithms actually stable. The first time you sort the last digit. So this is order, right? The second time you sort the middle digit. The third time you sort the most significant digit, right? So you can see once these are sorted, because stable, the order in the lower digits are actually kept, right? Because they're stable, they are already sorted in this subgroup. Okay, so you can see each time it's O1, right? So and you have 3n and you sort it. But this doesn't always hold, right? So because it's here, it's a 3 digits, right? In some special applications. And you may say that in computer science, we have integer like 46, 64 bits, right? It's fine, but just think about it. It's ON, right? You think you can claim it's ON, but you think about it, n log n, right? So Quicksort is better because this is 1 billion is 30. Okay, this constant is much larger than your log n actually. Okay, so in reality, if you have generic numbers, right? So we will just use Quicksort. Okay, if you know some special tricks, special properties of data, that's only 2 digits, 3 digits, right? We definitely want to use this kind of. Right. So again, we are not just theory people. Okay, what works faster in practice, maybe not so theory nice, but actually, yeah, it's faster. Okay, So we need to know these things, right? So now let's take a look how to solve things, right? So if you naively solve things, right? So write your own bubble sort algorithm that will kill you, right? It's n squared, right? And n squared and n log n, right? You know the difference, okay? You can cancel all this n first, right? And then you know the difference. Okay, log n is 30, n is a billion, right? A billion squared, you know it will not work, okay? Basically, for big data, we will not consider anything squared, and most n log n, right? And let me see. Yeah, so here is the sorting algorithm. You can see that what it does is that you have the iterator first, last, but basically you can search for subrange of that, right? And then you sort only this part, right? So this is actually used in quicksort, right? So you think about quicksort is really, hey, after this, I just sort these two ranges, right? Continue, right? So you can use this to implement quicksort, right? So, but in general, this is a function there, right? If you want to just sort the whole array, you put the first begin and okay, then you sort, right? And again, if your object is not a basic type, maybe you need to define your order, right? Less than operator. Okay. So here are some examples. Yeah, these numbers are not sorted, right? So if you want to sort them, you can say, hey, I want to begin end, right? Because it's already wrapped into vector, right? So then after begin end, I sort them. But remember, this is begin plus 4. This is not end, okay? So we are only sorting first 4 elements, right? Plus 4 means, this is 0 to 3, okay? 0, 1, 2, 3. 4 is exclusive. I don't want to emphasize more, okay? So it's always closed, open, okay, in all languages. Except for pandas, maybe some crappy programmers leave that there, and then this harms all the later versions. Okay? But for any professional, this is common sense, you can see, right? Everyone knows this, right? At least you need to catch up now if you don't, right? This is another example we are searching for from here, right? This time, this is inclusive, right? This is closed side, okay? So this is really 4, which is close to end. Keep in mind, end is one position after 80, okay? Right, so this is the whole range, right? Because it's exclusive, right? And so this is a sort of whole array, right? So these are the examples, and you can iterate them, but if you know it's array, you don't have to iterate, okay? So your class, semicolon, colon, iterator, you can get iterator. Then you can begin and you can iterate, right? There's also reverse iterators also. But for array, we don't need that because array, you can use I, right? You can use bracket, it's overloaded, right? It's the same thing. Okay, so again, what is this sort? This is basic quicksort, right? But actually they are implementing with some small tricks, right? So it's called intro sort, right? So they make sure that even worst case is n log n, okay? So because we know the quicksort worst case n squared, right? So it's a combination of quicksort, this is a major algorithm, right? Heap sort and insertion sort, right? Insertion of n squared, if you know, right? And so what it does is it begin with quicksort, right? But if your quicksort is recursive, right? So if a recursion, right, say you recurse, hey, I have this tree, right? I always follow this tree, right? I'm here, then I recurse on the left, I have a stack, right? And I have a not stack, this is a program stack we talk about, okay? Right, and then, hey, it sees it's too many stacks, okay? I go down to the right-hand side, it's become a list, it's not it's not balanced, right? So it's not binary search anymore, right? So in that case, I would say, hey, stop and switch to heap sort, okay? So this is kind of worst case handling, right? So most of the time this will not happen, but if the recursion depth goes beyond a particular limit, right? It may not be good. We should use skip sort. Maybe quicksort is hitting the n square atom complexity, right? And another thing is that if your element is less than 16, then we will just use insertion sort. Because insertion sort is even faster if even though it's n square, okay? You still want the insertion sort because, quicksort is kind of, doing a lot of back and forth swap, right? So this kind of swaps, those operations are very expensive, okay? Insertion sort, the complexity is expensive, but initially when it's small, sometimes it's even faster, right? So this is really the case for insertion sort. It's very fast, maybe due to cache locality, this kind of thing, right? So if less than 16, they will switch insertion sort, okay? Which is n square, but n square is still small, right? 16 square is what? 256. Okay, very small. Okay. And any questions? Yeah, if you have any questions, it's time to ask. Okay. And if not, let's continue. Right, sort in Java is the same. Okay, let me do it here. And as we said, so if you are sorting an array, you need to use utility array. Okay, sort, still you have the beginning, ending. You can sort in subarray. Okay, and this should be the array. And here's example, you sort them, right? So, and you sort array. Okay, if you don't specify this, in C++, it's not okay. You always need to say, hey, beginning, ending. Always get range. Okay, in Java and Python, you don't need, because this will be the begin, this will be end. Okay, it will have default value for you. Okay. Let me see what. Okay, yeah. So here's example, right? So if you have array sort, this array, it will be sorted. Okay, just that simple. All right. So the next one will be sort in descending order, and C++ has the same thing. Okay, so you can add something like collection or reverse order. Right? Then it will kind of use the reverse order comparator. Right? It's kind of because they have the internal less than operation. Right? It's kind of reverse it. Okay, just say, hey, originally less than is true, now everything false, right? So there's a way to just add another thing. All the language has this construct, okay? Just add another stuff to reverse it. And here's another example where we are defining a comparator, right? So comparator says, hey, I just compare with the row number, okay? So you can see this compare is really smaller than, right? Think about it, smaller than, you should return true, okay? Return a positive number. And let me see. Oh, this is actually larger than, right? So you can see when your row number is larger than B, you return a positive number, which means actually A should be before B, okay? Smaller than means A is before B. But actually, you know, A, when its row number is larger than B's row number, A is before B. Sorting wise, it's thinking small, okay? If that is the case, you can sort that, right? So here row number is 101, 131, 121, right? First you print them, it's really disorder, okay? And next time after you sort them, right? You sort them, and you need to new an object of the comparator, right? So both in C and Java, right? So you know that in C, if you have operator parentheses, and then this object, if you define the object for this class, it's a comparator, right? In Java, it's just comparator interface. If you implement this and you have another object, right, and you implement this compare function, you put it here, right? This you need to new a object for it, okay? And then it will function that for you. We'll call that. This basically will compare two elements within this object, okay? Call that function. And then it's ready in this 101, 121, 131, right? So let me see. Compare. Maybe compare should return. Let me see. Maybe I kind of have a vague impression. It's kind of, let me see. Compare return value. Okay. Yeah. So it means if you know, equal is 0, right? Less than is -1. Okay. So this is right. Right. Larger is 1. Okay. So here it's the same. Okay. But here it may not be. You do not have to be 1. Okay. So basically, if A's key is larger than that, right? So it's a positive number. It may not be exactly 1. Okay. It's just a 0 means equal. Okay. -1 means A is smaller. Right? If 1 means A is larger. Okay, so this compare is not the small and equal true or false. Okay, it's this relation in Java. It's kind of different. But so then this is still from small to big. Okay, it's all. And so yes, so similar to array sort, you can start the collection sort. Okay, so here's the example. So you have Arraylist, and you add elements. Here's our strings, alphabetic order. Okay, and you sort them. Right. So you can see D is before F, F is before G. right? And you can see the relation. Okay? If the first character is the same, you will compare with the second character. This is by default what is the collection.sort after that. In Python, right? Python has a sorted operator for you, right? If you have numbers sorted, it will return another a list. Okay. Keep in mind, sorted will always return a list. Okay. It will return another list which is sorted, but it will not change your original value. Okay. Your original, if you print the older one again, it's still not sorted, right? And so again, the input can be anything. It can be a tuple, it can be a set, right? But output is always a list. Okay, keep that in mind. Of course, it's a set, and you write the same value multiple times, right? So for a set, basically, it's the same value, right? It's just one file, okay? And let me see. So here is an example. For example, you can define a comparison operator, right? It's just like our comparator, right? You say, hey, I want to compare by words, right? So this is the key function, right? So key argument, okay? And hey, if I will use this function called the length to compare with, right? So this banana is has more characters than pi, so pi goes first, okay? So it's pi, book, banana, Washington. The longer goes later, okay? So every language has this kind of comparator, comparables, types, okay? And you can also reverse, right? Reverse go true, then you reverse it, okay? All these languages share the same idea, so you need to know from high level, then Google if you don't remember what it is, okay? And order values by sort, right? So there's another thing called sort, okay, in Python. But this is always a method of the list object, okay? Not any other object. You cannot have a set to sort, okay? Right, so only list can call this function. And it returns none, which means it doesn't return anything, okay? It's supposed not to return anything, okay? This is like a void, right? But you know, in Python and Java, we only have void star, which is, you know, we don't have really true void that can be returned. It's just a return nothing, okay? And it's update in place, right? So it means it's not like sorted, right? Sorted will not update our old value. It will return a new list too, okay? But when you call the list.sort, it will sort the list, but it doesn't return anything meaningful to you, okay? Any questions? So here, so when do you want to use sort and binary search? Right, so firstly, you have a static array, right? And we actually use it as stat. We don't use that sequence. Order doesn't matter. Otherwise, you cannot sort, okay? Right, so it has to be static, right? If it's dynamic, we will look at the binary search tree later, okay? Key cannot change, okay? The second is that you will have many queries, right? If just a query 1 or 2, right? So, you know, n log n is 30n, okay? It's not worth it, right? Okay, next is if we will frequently insert and delete keys, right? So in that case, we will use binary search tree, right? So because we will be updating, right? If you use just an array, what will happen is that insert something, you need to move everything larger than that towards the right, okay? It's ON. So only use it when your set needs update, okay? Otherwise, you just use array, okay? So the algorithm looks like this, right? So we only talk about simple stuff that you can get intuition, right? So complicated stuff, we'll get some high-level intuition and skip it, right? Because these are algorithm stuff, right? So algorithms are very important, by the way, but for now, for this training, it's programming training. Okay? It's not algorithm training, okay? And later we will have paper reading training really on algorithms, okay? We'll work on a project for basic Guimu will be leading on graph matching. It's really training you how to read papers. Okay, everything is sales tricks. Okay, paper reading, how to write papers, how to respond to reviewers, right? And how to do presentations effectively, right? So how to make those slides that you don't have too many words, only like 6 words at most, right? Okay, and with diagram, image, and actually this is super fast because I copy paste from web. Okay, I never write my own, right? But still more useful than you see other people teaching data structure. Maybe your previous instructor, everything is on this page, a lot of words, but you don't get anything, okay? Right, so there's tricks for everything, right? So we'll just do coding for you so that you know these libraries, you can call them quickly and understand what's happening down there, okay? Here, if you have a binary search tree, organize them into tree, right? So the benefit is that you can search, let's say we want a key, right? So what happens is the binary search tree it's always this element is in the middle. If it's smaller, you go to the left-hand side. If it's larger, you go to the right-hand side, right? So 8, you know, if you search for another element, let's say 2, right? So the first 8, I should go smaller than 8. I go to left tree, right? So if smaller, I go to my left. Okay, so this is like you have each node, it has 2 fields, right? So you have your value, but you have left pointer, you have the right pointer. Okay, if you are not pointing to anything, this will be null. Okay, if you have the node, you just point to that node. Okay, right? So this is how it's organized in C++. Right. So now we are reaching 3, right? Now we are currently node is 3. It's still not null. What we do is, hey, I still compare. Hey, 2 is smaller than 3. I should go to 1. Okay, so I will still run this. Okay, and now I'm at 1, right? 1 compared with 2. What happens is, hey, 1 is larger than 2. I should go to the right. Okay, right? So I will run this. And now the current node becomes right. I go back to while. Hey, right is null. Okay, because you know 1 is the leaf node. You have null here. You have null here. Right? And because it's null, what you will do is, you know, of course, you will find, if you find the value, you return this current node. Right? If it's you just search for 1, you just return. Okay. Otherwise, you return the current node. Right. So you can only return 1. Right. Because you only found 1. Right. And then you know, hey, 2 should be inserted as my right child. You can do that outside. Okay. Because this is search. This is not update. Okay. Or you can say, hey, my return node is not equal to my key. Right? I return 1, but I wanted 2, so this is not found. Okay, so anyway, so this is just a one search down the tree. So this is height. Okay, the search cost is height. Each time is 0.1. I just compare with the middle element. Okay, and insertion is the same thing. Right, so insertion basically goes through the same parts. Finally, we find, hey, this is null. Right, this is null. Then what we will do is we will create a new node. Right, so. By the way, this root should be the pointer, this pointer here, right? For that reason, we need to use a reference for the pointer. Okay, this is the reference. So this is saying that, hey, I have a node 1, I have my value, I have a left pointer, I have a right pointer, right? But when I call recursively, I put here root or right. Okay, this is the pointer's rename. Okay, right? When we say, hey, we come back again, root equal to this. This actually means this node, this pointer address variable. We are not creating new variable. We are using this one's right child, this variable. Okay, so that reference is very important. Oh, any question here? So in whatever case, it's really, you know, insertion, it's just a tree height. Okay, and you know, so here deletion is a little bit more complicated. So this may be the only a little bit more complicated algorithm that we cover, as well as the interview question I mentioned, right? How to split the quicksort, split things into 2 just by 1 pass. Okay, right? So here's an example, right? So if you finally locate, I want to delete this node D, right, all the way down the tree. Now I'm here. Hey, this value is the value I want to delete. I find they are equal, right? How do we delete them? Okay, so again, these things are designed by smart guys, right? So, but at least it's not difficult to think about. If you have no child, right? If your D has no child, of course you just delete it, right? So it's so simple, right? So it's the last node, right? On the other hand, if deleting, you have 1 child, right? Replaced, you know, remove the node and replace it with its child, right? So what it means is this, right? So let's say if you are finally C and you have B, right? Then C is deleted, right? It's fine. Your B becomes your parent's child, okay, right? And the more complication is if, let's say, you have 2 child, right? You have 2 nodes that are not null, okay? In that case, we do not delete D, okay? We will choose the in-order predecessor, or it's in-order successor as a replacement node, okay? For example, so the in-order means I first iterate here, and then I iterate node D, and then come back into the node on the right, okay? So in order to delete it, right? So you know all the nodes here are smaller. I'm in the middle. I'm on the right. Okay, and these are larger than D. Okay, in order to do that, you will find, hey, I will get E, right? So because if you come to this tree and iterate, right? So the smallest value is E. Okay, F is larger than E. Right? And if you find E, you just swap with D, right? And then you make F G's child, right? And it will not be possible that F is the left child of D, E, okay, because then F is smaller than E, and your in order smallest successor node is F, okay, which becomes this E without F, okay. Yeah. So that comes to the other case, which is yeah. So basically this is the operation, right? So you will not delete it. You will move this to here, right? Or you first delete it, okay. But before you actually just copy the E's value here and then delete E, okay, and then make F G's keep, okay. Right. So you will always find the lower left corner of the point. Right. So if you have E has a child, it will be going to be the right, okay. Any questions? Again, binary search tree is not sufficient, right? This is the best case, right? So best case means, for example, it's really log n. It's really binary search. But if you want to look at tree structure, we can also do that. This is 1, 2 to the point 0. And this time you have 2 to the point 1. And this time each one you get 2 more nodes, 2 to the point 2. Okay. And then the next layer is 2.3. Right? And let's say we have height edge. Okay. What will happen is it's 2 to the point 0 all the way to 2 to the point edge. Okay. So that value, you know, last time I talked about it. Right? So the first item is 2.0, which is 1. And then 1 minus q, okay? And 1 minus q to the power edge, right? And here q is what? Q is 2, okay? Right, so this is really minus 1. This is 2 to the power edge, 1 minus 2 power edge, okay? And really, if you reverse them, right? So it's this plus 1 compared with the 2 power edge, it doesn't really matter. Right? So if you take out this, it's a minus 2 power edge, divided by minus 2. So it's minus the cancel, and along with the 1, this is really 2 to the power. Okay, right? So you can see that, you know, for 2 to the power edge nodes in this tree, your height is just edge, right? So edge, let's say this is n. Okay, so 2 to the power edge is n. So many nodes, right? So this node, and sum together. So n is really what? H is really H is log 2. Okay. So this is how you divide the log n bound for the tree. Okay? If it's balanced, it's a complete tree. Okay? But what can happen is that it's not balanced, right? So in the worst case, it becomes a list towards the right case. Right? In that case, it become an array. Okay, it's not log n, it's n. Okay, so that's why in data structures that smart bees talking about, you know, so-called self-organizing balanced binary tree. So let's say you insert, you keep insert, hey, you find it unbalanced, right? So what we will do is, hey, I will reorganize this score into this, right? And then the height is smaller and it keeps the logging bound, okay? Edge is logging bound. Remember the edge is the insertion, deletion, search, they're all logging. Okay? It's unlike an array. Array is O1, O1 for append, right? So, but insert is ON, right? Here it's all logging, right? And O1 for append, log n for search and intermediate item. But when you insert delete, it will be O1. Right? Now maybe you cannot append with O1, but everything ON. Right? If you add elements into a set, it's always ON, log n. Okay, but everything is log n. Right? So everything inserted, you will not have some operation become 1 billion. Okay, so this is the idea. Right. So let me see. Okay, so you can also reorganize this. So how does it work, right? So basically, there are data structure clauses, right? So these are algorithm people work on the left to right, right? So you can see that this is alpha is less than this and less than beta, right? And then less than gamma. So alpha less than beta, less than gamma, okay? And if this happens, we can rotate a little bit, right? So pull this up, pull this down, right? So it still keeps the ratio. Alpha is less than beta, less than gamma, right? So right is larger than left, okay? So, but this operation doesn't change any requirement for binary search tree, but it can balance the node. Okay, so there's some reason. Let's take a look at this animation. Okay, insert. After insert, hey, this is not balanced, organized, right? So this is AVL tree, by the way. Okay, hey, we organize. Yeah, we keep some. You can -1, -2, right? So it's how much data you own, right? If you own too much data, it will organize, make it the data clear, right? Because maybe you are imbalanced compared with the other branch, okay? So the detailed algorithm is very complicated. Very smart people think about them, okay? So, but you understand the idea, okay? So each time you do some upfront cost, updating, right? And then you make sure each time you can still search for it. This is similar to what we talked about size, right? Each time if you append, you size plus. Then when you want to get size, you can get it in all one time, okay? Right, immediately you get size. You don't just scan the array. So this is too long, don't read. Okay, so usually, so this is what I will not put the algorithm here, okay? And similarly, this is a red-black tree. Okay, so there's another scheme, right? There's a lot of schemes like this, okay? So they will define how many red node is on this node, how to balance, okay? There's different cases. So these are the algorithm people, okay? So it's very smart people, okay? And there are different cases, and each one you make it work. I still log in, keep the relationship. Okay? Again, too long, don't read. Too complicated, don't read, okay? But you know that it's, what's it to do, okay? It's keeping everything like a binary search path, what you can insert, okay, or delete. Right, so here are C focus library. It's called a map. I think a lot of you potentially have used that, right? So for map, you need to define the order, which is less than relationship, right? And it will return you a pair, right? The key and the value, right? You know, sometimes you DOR first, which is key, DOR second is value, okay? It's a pair structure. Internally used as a map. Any questions? There's an internal comparator object, okay? And a comparable map, there's a hash map, or we call an ordered map. In C++11, they standardize into an ordered map, okay? And actually, we will keep in mind, this is a red-black tree, still need a 30 hops, right? An ordered map is even faster, right? Map is slower than an ordered map. But an ordered map will use more space, okay? Because it's hashing. We will talk briefly about it later, because we're not going into the details. Hashing is even more complicated. It's kind of randomized out, okay? And so, yeah, so directed, no, you can iterate on a subset. It will still keep the order. Iterator will keep the order, okay? Because it's basically based on the order, right? So left go to left child, right, larger go to right child, okay? And a map, here, map can use an operator, okay? It's just like array. But this operator is not so simple, okay? When you let's say, in your map, you say, hey, I want this key. What it does is it's doing this for you, okay? It's doing this for you, right? So the bracket is running this code. It's operator overload, okay? It will find one, go, hey, one, and return this line, okay? Equal, return this. It's log n operation, okay? Keep that in mind. Let me see. Potentially should clear this and use this again. Right, so it's a map implementing binary search tree, but actually it's a balanced. This is another source, right? So it's actually the red-black tree, okay? Right. How it works is not important, right? So you understand what's happening there, right? So another thing is that, remember, if we want to see a get element, right? So we need to compare, right? So really, you just need a less than, right? If A is not less than B, B is not less than A, then it's equal, okay? You only need to compare to say it's less than, okay? So by default, it will use the less. This is the default template if you don't get anything. And so this operator is really doing something for you, okay? So operator here is different from add, okay? So this is added in C++11. So let's take a look at why I want to particularly talk about this operator, okay? So if key cannot be found in the container, the function will insert a new key for you, okay? Right? So that means, hey, you can just say, I want a D5 equal to something, right? And the D5 will be inserted, right? You can directly access it. If it's not there, it will use this default constructor of a value to create a value there for you with that key, okay? So that has a side effect, okay? This is different from map.add. Map.add will throw an exception if you cannot find a key, okay? And internally, it's doing something like this, right? Insert, right? So you can see this bracket for you, when you, like in Python, you call a bracket a key, right? Internally, it's doing something for you, right? Like the insert, and this insert operation is really, you know, the tree traversal here, okay? If you don't understand these things, yeah, you don't understand common sense for good programs, okay? But in Python, it's a hash table, by the way, right? So yeah, here's an example. Why you can do this, right? Why you can do this, right? Because if it's not there, it will create an empty value for you, and then you copy the value this here. Okay, so you can do this, right? If you are so this has a side effect, right? So what happens is this, right? So what if you want to decide whether value is inside there or not? Let's say you have for A, B, C, D, right? And then we want to check whether B is in there or not, right? You have to use find. If you directly check a map D, B, it will create an empty value for you. So it has a side effect. If you just want to see whether something is in the map, you have to use this find function, okay? And like before, if, and means everything after this, it's in order traversal of all elements so that it's keeping the order. And the end means one after the last element, okay, rightmost element, right? So if you cannot find it, it will return the map n, okay? So basically, so if you cannot find B, it will return the map n, okay? Which means you cannot find it. Right? If it's not map n, it will return this iterator to this object, key value, okay? And then you can erase it. Okay, so these are some typical things that you can do. So this map will not have a side effect of insertion. If you are calling the bracket, by default, it's not just searching, okay? It's insert, okay? This is very important. You need to understand this, right? All right, let's go back to Python, right? So Python has this dictionary object, right? So, and if it's string, you can actually also do this, right? Usually what you do is key value tuples, right? And once you create this dictionary, let's say, here you don't have Toronto, right? So if you search for Toronto, it will say, hey, there's no key, right? Error, okay? So what does this mean? What does this mean? This means Python's bracket operator will not insert for you, okay? It will just report an error. This is different from C, okay? Every language still has some difference. Keep that in mind, okay? So they are very important, okay? If you assume C, what happened with C, it also happened with Python. That's trouble, okay? So key error, you cannot find it. It's just assertion, it's not insert. Okay, so, yeah, I think, yeah, if you are not able to continue, you can just watch the video, okay, because we have the video. I think MATLAB, I think, right? So anyway, so this is just a training for you guys. Okay, I think if you listen, it's kind of push you to listen, right? So otherwise, watch the video, you may just get a 30% or 20%. Sometimes I will ask you a question. I'll give you some pride so that you will. Let me see. Oh, because I use the pen again, I have to. Right. So again, so here this can be done. Okay, this can be done. Even if Kansas City is not there, you can call this. This is built in Python. Maybe in C also, right? So if you have this equal directly follow this bracket, it will not call the default constructor to create for you in C. It will just take this value there. Okay, using this key. Right, this is insertion. So this equal maybe is insertion. Let me just verify this with you guys, okay? std. I think there's an operator overload. Yeah, so you see, so this operator overload. Okay, so basically there are some like initializer, you see, initializer value. Okay, so this is actually, it will, since CPUB's 11, you can do that. Okay, so it's basically calling insertion down there. Okay, so but this is Python. It's the same thing. Okay, but Python here, it will not call insertion for you, right? So here it will call insertion because of equal. Okay, so it's not because of the bracket. Okay, and then let me see. You can replace the new value with an existing key. Okay, and you can delete the element. If you want to delete element from dictionary, just give dictionary and the key. You delete it. Okay. So if you here the inner works. So I give a warning. So Python, you don't have red black tree. Okay, it's always hash table. I will talk about later. Okay, and yeah, this is at the top. Maybe it's blocked. Okay, and if you look at so Python, right, it's super inconvenient sometimes, okay, because sometimes you want to do a counter, right? And the first time, if you find it's not there, right? Let's say A is a counter. I want a plus equal to 1. Okay, Python has no plus plus, by the way. Okay, but if the first time I call this, what will happen is it will tell me, hey, I don't have A key, right? Then I have to create a, whether it's already there, it's not there, we create a 0 with key A with value 0. Right? This is not convenient, right? Python has another saying called the default dictionary. Okay, so let me briefly explain what to do. So default dictionary is an override dictionary. You can have default factories here saying, hey, what value you want to get, right? And then you can do this. Then this becomes our C++ bracket. It will insert for you. Okay. If it's not there, it will create 0 for you. If it's a number, it's a count. Okay, because the default constructor will. Here's the example, right? Now we say, hey, your constructor is integer, right? So when you create it, we'll give it 0 here. Okay. Now we have these values. Now we can just write a for loop and a plus equal. Okay. Right. So for example, this 2 appears once, twice, 3 times. Right. The first time it appears, it will automatically create in the dictionary. Okay. Create a key is 2, value is 0 using this constructor. Okay. So now it appears, it will call this plus equal to 1. Right. Oh, actually, after constructed, it will be equal to 1. The next time it will go to 2. The next time it will go to 3 because you can find this key there. Let's say in your red black tree, but Python again it's hash 2. Okay. It's kind of similar, but it's different structure. Okay. And in Java is the same thing. We have the tree map. Okay. In C++, it's succinct, right? So it's tree, no tree, right? So map itself, right? So here Java it emphasizes its tree map. Okay, it's red black tree, and you can still have this whether this is contain key search, right? Get, put, remove. Okay. Keep in mind Java cannot overload the operator, so you don't have the bracket. Okay, that's super painful, right? For example, if you want to insert, you are not saying hey something Greek 3 equal to Greek, right? You have to do put, and then you have to call get. Okay, so that's why I so much hate Java. It's just so long and so not user friendly to read. Right? So if you can speak in 2 words, Java will tell you in 5 words or 10 words. Okay, this is Java, right? And here's an example, right? So you define tree map. This is key, this is value, right? And then key value put, right? And then you can get you can iterate through. Okay, so every language has its iterator through the container. Just Google that and you will find it. Okay, how to do that. Let me see. And this is in order traversal, right? So again, pay attention. Here, this is not a binary search tree, okay? Because left is larger than the middle, okay? So and this is also larger than middle. But this is telling you what it means by in order traversal, right? When you traverse a tree, it's a recursive operation. You first traverse the left. Let's say I'm at this node. I will first traverse this node, then I traverse this node, right? This is the current route, and then I traverse the right. Okay. And when we traverse the left node, what we do first when we are at 1, right? What we will do is we first traverse. We will traverse 2, right? But when we traverse 2, it's a recursion process. We will first traverse 4, and then we traverse 5. So what will happen is we will first go 4, and then the middle, and then go to right. So this is the in order sequence of the tree. Okay. So as an iterator, iterated O1 cost per time call you go to the next, right? From here to here, this is kind of not so intuitive, but actually they have a way to do that. Okay, this is very smart, right? So there are a lot of algorithm smartness that I'm not covering, but you need to know intuitively what they are doing. Okay, and all the data structures are not possible without pointers. Okay, everything is pointer, right? So hiding the pointer doesn't solve the problem, by the way, right? Like in Java. Okay, so you need to understand it. Okay, so let me see. So for example, the pre-order will be you first traverse your current node, then 1 and 3. Okay, so you will first heap up 1. Okay, and then we go to this tree and this tree. That's why you have 2, 4, 5, and 3. Okay, in order heap, first traverse the left-hand node, right? 3, 4, 5, and then come to 1. Okay, but if it's actually the binary search tree, which left is smaller, this is the middle, this is right. If you do in order traversal, okay, in BST, binary search tree, it will be in non-decreasing order. Okay, any question? Yeah, today we will be a little bit longer because we have about still like 20 pages. Okay, I will go a little bit faster. Okay, so this is again the same thing. Right. So keep in mind, one thing very important is that iterator, okay? If you do the iterator in your tree structured stuff, okay, it will always keep the in order, okay? It will go from smaller value to the larger value. Its iterator is just an in order traversal, right? O1 each time. The algorithm is very complicated, not so complicated, but need some time to think about these 3 lines. Okay, so I will not go there. But you can see if it's a tree map, for example, let me see. So that's the reason why I'm doing this here. Key is ordered 1 traversal, right? So if you have this thing here, this key 3, 2, 1, it's really 1, 2, 3. Okay, you have this guarantee here if you use a tree map or map in C++. Okay, right. So tree set. So again, I haven't talked about what's the difference between set and map. So by the tree, you have the key, right? And set is just you have the key, okay? Right. Map is besides the key, you attach your value. Okay, there's no difference besides that. All you care about the key when you compare left right. Value is something attached with the key. Okay. And so you have the tree set where you can use add. Okay, so this is I think in Java, right? So you use add. Okay. And if you use C++, you insert. Okay. I would like to be a little bit quicker, but let me see whether C++ is always something a little bit more interesting. Okay. So if you look at the operator, it's more powerful because it's more low level, right? So you can see that insert a value. Let me see. You can insert a value, right? So like this. You can also do insert. You can capture the return value. So return value is actually you have a pair, first and second. Okay. First is the iterator pointing, right? So it's really where it points to because it's a set. It's really just point to the key. Okay. Here. But there's also a second element, right? The second is true if the element is inserted. False if it already exists. So you can use this to determine whether it's already exists, right? So if it's here, then means false if it's already exists, means it's in the set, right? Then you can get it, right? So this is because maybe in the set, you have this element, right? So, but you want to attach some additional stuff to the set, right? So maybe it's not in the form of key value, it's an object, so you have some additional field you want to attach. Then you need to get a pointer of it, right? It's not just the value of it. It's not a deep copy. You want the pointer to it. Then you can get the first time, okay? And you can also insert, right? So insert, like here, we just insert a value. Why we care about this insert, right? So this is because, remember, we are doing the tree traversal, okay? If we come back to here, right? If you are doing tree traversal, last time, let's say, last time you traversal to here, okay? And you give this operator as a hint, and then you say, I want to insert 7. It will use O1 time iterator to here, okay? If you don't give it, it will be log n search, okay? So that's it. If you give the hint, then continue, and you say, I want to get to 5, right? If you give the hint, it will be O1 time to search, right? So this is the idea. So you can see this is called right. So this is called the max efficiency insert. Max efficient, no max efficient. Why? So because the 25 iterator, right? This iterator is right after 20. It's very efficient, right? So, but if you go from 24 to 26, right? So it's kind of already go past that. This hint is not so good, okay? So this hint is at the position. Oh, we saw the iterator, right? It should point to the element that will follow the inserted element. Okay, it's actually what I described is wrong. Okay, it should be follow the insert element, right? So it should be the next element to insert element. Then it will insert something before that and maybe do some adjustment, right? So if you come here, when insert something here, right? So you should give this guy, right? We give this guy, this will come here. This will adjust a little bit, okay? Rotate or something, right? So this is the idea. So yeah. And finally, you can insert a bunch of them, right? When you insert a bunch of them, you can see the time complexity, okay? So 5, 10, it's different from inserted 3 times, okay? It's actually size plus n, right? Because if you have a insert and the rest of them, you can scan them, right? So you can follow the in-order traversal, right? So this is more efficient. Right? So instead of each time you go log n, the first time you want to find the 5, you need to do log n, okay? So there's some optimization, but usually you don't go so complication. All that you need to use is really the first one. Okay, just insert. Okay, a lot of time you are just see whether the values really appeared before, and you don't care about how many times it appears. Right, you use the set. Okay, just use insert, and you can get its iterator. Then you can also erase it. It's like a pointer, right? It's like a node in the tree. Okay, then you get a node. You find it 20, and this 20 is here. This is a node, and then you get erase. Erase, you delete it, right? And remember, I would erase or do some complex operation right before. Okay, so that's not so trivial, but to you, they are all implemented for you. Okay, in those libraries. All right. So next is besides that, you can also have multi-set. Multi-set, the difference is that you can appear, let's say, the same value multiple times. Okay. So for example, in that case, you can actually use another function called count. Okay. This appears 3 times. 1, 2, 3. Then if you give a count, it will say 3. Okay. If you use just a regular set, okay, both are in this include set. You can use set. You can also use multi-set. But if you use a regular set, it will always be 1. Okay, because it avoids redundancy. Right. In implementation-wise, it's also very simple, right? So you just steal this key 73, right? But you append a list of those values with that key. Okay, you keep multiple copies of them as values, right? So, and here, yeah, you also have multi-map. Okay, if you multi-map, then you have multiple keys. You can have the same keys, maybe point to the same value or different values. Okay, you can have multiple copies of them. And so Python, right? Python, again, we need to emphasize it's hash table. It's not red black tree. Okay, Python is hash table, different. Okay, all we talk about so far in C# and Java are trees. Okay, and hash table, it's again add. Okay, in C++, insert. Okay, set.insert. In Java, it's also add. Okay, in Python, it's also add. Okay, so an item added to set, just add method. Right, so you know add is a tree traversal, right? Login. Okay, but here Python is a dictionary, right? So it's a hash table. It's different. Okay, we'll talk about it later. Okay, add multiple items to a set. Right, so you will use update. So when you update, you give a list. Okay, if you use add, you just give one value. Right, so that's the difference. And the in operator is very important. Let's say you have a value A in a container. Right, this is what I say. If this is gonna be very expensive, this is very big, even if it's a list, try to make it a set parentheses, okay? Because then it's fast, it's a hash table. Otherwise, you need to, each time you call this in, it's scanning for 1 billion elements. Now it's just scanning for maybe 30 elements, okay? And hashing counterparts. So hash table is something like this, right? So you hope you create enough buckets so that when you insert elements, and they will hash to a key, right? There's a hash function good enough, and after modulo, they will hash to different places, right? And if there's a conflict, of course, you have to give an adjacency list. You have to give a list to track all these values, right? So for example, now I want to search for ABC, whether it's in a set, right? What I have to do is I hash it to 980, and the modulo value becomes 0, and then I search for the list, right? So it's really a hash is 01, and followed by the list length, okay? Right, a scanning of the list length. And there's proof that if you adjust this size large enough, and the hash function is reasonably designed, okay, this list length will be 01, okay? The constant, maybe 4 or 5 elements at most, right? So that's why hash table is faster than tree traversal. Right? Tree traversal will search for 30 elements, right? Hash table maybe 2 or 3 elements in the list, okay? So that's gonna be faster, right? And you may ask, if I insert too many elements here, right? So I insert many elements. Then this bucket, there's a lot of conflicts, right? So don't worry, just like array, right? Vector, it will resize, recreate a new bucket for you. Maybe now double to 8 buckets. Again, you have a lot of conflicts, a trigger, and a double to 16. That's why I say the space cost is huge, okay? So let's take a look at here. So this is what it says, okay? So if you use hashmap, okay, the keys, search, insertion, removals, operation now become constant on average. Okay, you can have the worst case very bad, right? The list very bad. but on average, it's constant, right? It's going to be better than log n, okay? But you pay the space cost for it, okay? You have more buckets so that you don't complicate, okay? So this is all high-level ideas. The low-level analytics is very complicated. We don't want to cover that here, okay? And you are using hashing from time to time when you call dictionary, right? So all these data structures are already being used by you, okay? Without being noticed, right? And so not sorted in any particular order, right? So which means you cannot assume if you iterate them, what it's doing is when you do iterating, right? For example, you are iterating a container like this, there's no order to, okay, it's iterating the first bucket and second bucket and third bucket. It's not like a set or a tree set, okay? There's no order between the elements, okay? Because this hashing shuffles all the elements, okay? So keep that in mind. You iterate all the elements, you guarantee everyone will be passed once, but there's no order there, okay? And elements cannot be modified. This is mainly the key, okay? Value can still be modified. Otherwise, what's the point of map, right? So set you cannot modify because all they have is a key. Okay, so there's no value. Okay, so let me see. Yeah, so this is an ordered set, an ordered map. This is a counterpart for set and map. The usage is basically the same, but internally it's different thing. You know that you cannot iterate a guaranteed order, okay? Otherwise, it's basically the same. The difference is actually, there's still different, right? So you can see this hash really care about whether you equal to that key in the bucket, right? Whether you map to that bucket. So it's not a comparator, it's not that. Okay, if you have your own object, you need to define this function for it in order to use the hashset, okay? Or the set. So that's even more complicated. So unless you're necessary, you can search for that. Otherwise, usually, yeah, so I will teach that maybe sometime later to my students. Okay, if you have your own user product stuff, right? How do you define it so that it can be used with a hash set, right? An ordered set. Okay, and for Java it's very simple, right? So for object it has a hash code function, and you just overload the hash code function. It will then you can use a hash set. Okay, so Java is called hashset. Okay, and also add, it's the same thing, right? And you can also use hashmap. Okay, and key value and put and get. It's the same thing basically, right? So it's just using maybe 10 times more space, but maybe much faster, 10 times faster. Okay, and if your space is enough, then why not, right? So Python just like do away with the tree structure. Everything is hash table, okay, right? And so you can see that if you define them one by one, it's all not preserved. The pet dog can go to the second place, even though it's at the last, okay? So Python, you don't have the tree set, right? So if you want them to be ordered, you have to sort them in some way, right? Sort by key, get keys and sort, right? And that's almost the end. Let's quickly go through the last few things. So database indices, right? So now if you have objects that you cannot save in the memory, you want it on the disk, it's the same thing, right? So you have the B plus tree, right? It's the same thing you want to save. So there are two differences. One difference is that now instead of just a binary search tree, left and right, okay? Now you have a lot of keys here. And then you have a big fan out. This is because each time we read one integer, or we read 10 integers, or we read 4 KB of integers. It's the same cost from disk, okay? So why not we just make a fatter node? Then each time we can cut into smaller pieces so that when the tree is fat, right, the height will be smaller, right? So log 2n is gonna be taller than log 4n, okay? Right. So, and another change is that you can do range query, right? So you can go to here and then you can say, I want to find all elements from 11 to 41, then you can just follow this to 41, right? So this search code is log n, okay? After that, this is how many elements you want, n, okay? It's log n plus n. You cannot do better than that because let's say log n is only maybe 3 in this example, okay? Right, so load this node, load this node, load this node, 3 disk loads, okay? But you want to return, let's say, every number, you want to return 100 integers. You cannot just paste 3 to return, right? So at least you need to put them into the return result, right? So this is actually also minimal, okay? So the search for the first element and then goes through every element once. So it's log n plus n. Another case is called R-tree. Okay, R-tree is for spatial indexing. What if go beyond the one dimensional, right? And go to two dimensional, right? So R-tree is kind of this structure, right? So this is the first level node, this is the second level node, okay? And bound together, right? It's like a B tree, but two dimensional, right? So for example, if you do a range query, if you have an R-tree, okay, what you do is, hey, whatever overlap with me, I check. For example, the first level, maybe those two red nodes both overlap. So, but once we check this node, the second level finds this P is not overlapping with me. I don't even need to check any CD below it. I quickly prune those nodes, okay? But R-tree has no log-n performance guarantee, unfortunately, because once go to 2D, there will be some overlap. It's unavoidable, okay, if you do recursive upward, okay? And when you insert things, R-tree also supports that, right? So what it does is, for example, if you insert something to here, right, it will check, maybe I should enlarge this bounding box to include it. This is going to be cheaper than if I enlarge this, right? You can see how much enlarge, right? And then you decide which one is more economic, okay? And yeah, so there's also R-tree best first search. What it does is that you can maintain a priority queue. Each time what you do is you can compute the minimum distance from your query point. Let's say you do nearest neighbor query, right? Closest point is here, then this will go to the first, okay? And next will go to the second, okay? And then the first will be popped, and what you do is now the next layer, you have these two nodes, right? And then this time when you compute the closest node, maybe the distance will be a little longer, right? And then by priority, you will go to lower. Then you will check this, okay? So by this, you can actually expand only the necessary node. It's almost a minimal node that need to expand given this structure to reach the nearest neighbor, okay? Those far nodes, you will never access them, okay? Because they are so low in the priority queue. They are at the top level, right? They are not expanded. You don't touch those many low-level nodes, okay? Each time you only touch those that are closest to you in terms of the closest point to you, okay? So this is the concept. And there's also KD tree. KD tree basically kind of k-dimensional tree, right? But in two-dimensional, it's doing this, right? First, you cut here so that there are approximately the same number of points here, right? Then if you look at the left-hand side, right? So you will find a point on the other dimension here, and so that there are approximately the same number of points here, right? And then if you look at this node, you will cut again, right? So you will do the same here also, and that's here, right? So each time you do this, and you can see really it's a binary search, right? So if first you see X, you're here, then the next level you need to see Y, and Y is again you can cut by half, okay? And then X cut by half. It's again binary search. So this KD tree has a performance guarantee, right? And there's also so this is a nearest neighbor. You can also do the KD tree. For example, if you wanted to find nearest neighbor, and this is so close to you, just like R-tree. You already find a point which is very close, right? And you notice this you will never need to check it because this closest distance is already larger than your nearest point, right? So you cannot find a closer point to this, okay? So there are detailed algorithms there, but we will not cover that, okay? And this is kind of outdated research. It's too mature. Maybe 10 years ago, it's still very hard. I do a lot of research in this area, by the way, okay? And there's a quad tree. Quad tree is saying that you can tune to the density. Let's say if you have dense, you can continue to cut. Right? Here's not much, too much, you don't continue to cut. Right? If here there's too much, you continue to cut. Each time you cut by 4. This is actually used in complete graphics, right? So it's kind of this structure. And then with this structure, you can also do this kind of range query. If it does not overlap with you in that box, you don't need to continue to check the subtree inside that box, right? And for nearest neighbor, then you see, hey, if your current nearest neighbor is already, the distance already closer than your distance to that box, okay? The closest point in that box, then you can drop that box, okay? So these are the ideas. There's also range query, right? So if you just have one-dimensional range instead of two-dimensional range, you can use interval tree, okay? And you can use segment tree. They're all there. I think Jala has used the interval tree in Java, in Python, right? And why we want to use these, okay? Because they're performance guarantee, okay? The performance guarantee is firstly find the O(n) cost because there are so many elements, right? You find the one particular segment with this range, so you cover with your range, and then here, all these ranges cover with your range, right? So you want to return, this may not overlap with it, because these 4 should be returned, okay? These 4 are M, okay? M is reporting M intervals, okay? So of course you have to pay 4. So this is you want to return 4 elements, you definitely need to check them, right? And put them into the output, right? So this is the minimal you need, right? The other is log n, okay? Log n is, you have a billion intervals like this, right? So how you just, first thing you zoom into this region, which is 30, and then you know, hey, those overlap with this range has 100 of those intervals, right? So small intervals inside overlap, and this plus 100. That's the asymptotic cost, okay? The actual cost could be very big. So this is called output sensitive, which means it's almost dominated by your output, right? So the log n is just 30, right? But your output may be 1,000 of those intervals that you then check. So it's really dominated by the output size. This is called output sensitive algorithms. Okay, that's pretty much end of today. Okay, all I need to let you guys know is really log n, okay? And try to use data structures wisely. Any questions? If not, that will be the end of the training. I will put the slide and the video online. Okay, so if you want to watch it again, you can take your time. Thank you.
Thank you.
Bye.
Thank you.
Thank you, Professor.